Okay, so this is 4.6. This is variation of parameters to solve a non-homogeneous differential equation. So we use the variation of parameters when the method of undetermined coefficients cannot work. So I'm going to show how variation of parameters works for a first order linear differential equation, but we don't use it for a first order linear differential equation. We use it to solve a second order differential equation or higher. And later on, we'll even use it to solve series solutions. I'm starting with the first order because it's a lot easier to show you how to solve it algebraically, and then you can see how the second order works without actually proving it. So let's look. Our general solution for this is going to just have one parameter, C1, since it is first order. Let's start off with YC, the solution to the homogeneous DE. It'll be C1 times our solution, Y1x. So Y1 is a solution to homogeneous So Y1's a solution to our homogeneous. So when you plug it in, you basically get 0. So now our particular solution, just like we were doing in the last section of undetermined coefficients, we will choose YP. Since we're going to use Y1 of x, we're going to have to make it independent of YC, so we will use U1 of x. Again, this particular solution has to be outside the span of the homogeneous. I know we were just multiplying by x in the previous section, but we're going to just multiply by some function of u1 of x, and it will be independent now. So since this is our solution, let's go ahead and plug it in to our first order non-homogeneous GE. So we have to plug in our first derivative also. So y is our solution. We'll just call it u1, y1. We know they're both in terms of x. So dy dx, we have to do the product rule. And now let's plug it in. Plugging it into here. So instead of y, we'll write u1, y1. I am going to rearrange these two. And these have u1 in common. I'm going to factor that out. Just copy everything else. And if you notice, that is the same thing. That's our solution. Y1's a solution to our homogeneous. So this is 0. So the whole thing's 0. So we get u1 prime y1 equals f of x. So we can solve for u1 prime. So not really too worried about memorizing what this is equal to, but remember our solution, once we find u1, we have found our y particular solution. So all we would have to do, integrate in terms of x, and there's a formula that we have for u1. But again, this is for a first order DE. And my yp would be u1, y1, and where y1 is our solution to homogeneous. Which is the corresponding homogeneous. Okay, so now I want us to look at, we want to do the same exact process for a second order, linear DE. We do start it off with standard form. So this is our second order linear differential equation. It has to be in this form, leading coefficient of 1. And we're going to assume that we have y1 of x and y2 of x. So we have two solutions. Is our fundamental set, which forms our homogeneous solution. That means my yc, which is my homogeneous solution, is yc equals c1 y1 plus c2 y2. So what we're going to do to find yp, we're going to choose yp, same idea. Instead of constants, we're going to make each of those independent. So we'll do u1 y1 plus u2 y2, where u1 and u2 are functions of x to make those independent. And once we can solve for u1 and u2, we basically have our particular solution and our general solution. We add them up, and that's our general solution to the non-homogeneous DE that we started with, this one. Okay? So in order to make this happen, I'm just going to start it off. I'm not going to actually go through and do all the algebra for it. It's not hard. yp equals u1 y1 plus u2 y2. We will have to find our first derivative, take the derivative, use the product rule twice. And then we will also have to find, that'll be 4 terms, just so you can see where I'm going with this. We have to plug this into our DE, or non-homogeneous DE. Same process as before when we were equating coefficients. And then, so we will have 8 terms, right? 8 terms. And we will plug it into here. And we'll simplify it. And what will come out, so we plug this in to DE. And we do a little bit of simplification. And what comes out are 2 equations when we equate. y1 u1 prime plus y2 u2 prime equals 0. And y1 prime u1 prime plus y2 u2 prime equals my f of x. Okay? I don't know if you recognize this, but we can rewrite this as 2 equations, 2 unknowns. These are our unknowns. u1 prime and u2 prime. Just like in the previous, when we did it for the first order. So we will have a matrix here. And sorry, that's a prime there. And we have our B. So again, remember y1 and y2 were our solutions of our non-homogeneous. That's how we get this started. This, does this look familiar, is our Wronskian. And since y1 and y2 are independent because they are solutions to our, it's the definition of solutions to our homogeneous, we can use Kramer's rule to solve this. And we want to be able to use it to solve for u1 prime and u2 prime. And then we'll be able to integrate both sides and solve for u1 and u2. And once we find u1 and u2, we have our particular solution. Okay, that's our goal, is to find u1 and u2. So using Kramer's rule, this is our W. So the W, the Wronskian, is actually the determinant, which we know is going to be non-zero because Those are independent. That's what the test is for. The Wronskian tests for the two functions at the top being independent. And W1, we know that's not equal to 0, so we can use Kramer's. So W1, we take our B, it goes in the first row, and Y2, our second row stays the same. And W1, and our W2, our B goes in the second row for W2, and our first row stays the same. Our first row would be this row. So U1 prime is W1 over W, and U2 prime is W2 over W. And then once we find those functions, we just integrate both sides to integrate both sides to get U1 is equal to integral W1 over W dx U2 W2 over W. Again, we're not looking to memorize this formula. We do want to memorize the two equations that it creates or just the linear that it creates. You want to remember that our unknowns are actually U1 prime and U2 prime, not U1 and U2. And then we use Kramer's rule to find U1 prime and U2 prime. Okay? So I would like to actually just recap the whole process before we do an example. Used to solve non-homogeneous linear DE. So we first solve the homogeneous, the corresponding homogeneous, to find our fundamental set. And I'll just call it Y1, Y2, two independent solutions to our homogeneous, the corresponding homogeneous. And then we're going to construct YP equals U1, Y1 plus U2, Y2. And we're going to not do all the algebra. It comes down to two equations. That one's 0 and this one's f of x. And then it creates the linear algebra setup, y1, y2, y1 prime, y2 prime, times u1 prime, u2 prime, equals 0 f of x. Again, that's our f of x that makes it a non-homogeneous on the right side. And my third step is to solve using Kramer's rules. And the Wronskian, using the Wronskian, y1, y2, y1 prime, y2 prime is the Wronskian. In W1, we replace the b. This is the determinant. 0 f of x. The first row, second row stays the same. y1, y1 prime, second row stays the same. And we found our u1. u1 prime is w1 over w. u2 prime equals w2 over w. Again, I remember your Wronskian, which is your A. You can't use Kramer's unless this is not equal to 0. And so you want to remember that that is on the bottom because it cannot be equal to 0 to use it. And then my fourth step, we integrate both sides to find u1 and u2. And then so u1 is the integral of w1 over w, and u2 is the integral of w2 over w. And my fifth step, my solution, my particular solution, once we find u1 and u2, and my general solution is my homogeneous solution plus my particular solution. So my general solution is, this one is C1Y1 plus C2Y2 with the constants in the front, parameters, plus my YP, just copy it from what I just found here, right? And that's how you do it. So let's do an example. So we're going to use the variation of parameters. So we first find YC, the corresponding homogeneous. Constant coefficients. So we're going to plug it into there. So I'm going to go ahead and factor that out. We get r squared plus 1. So we can see r squared equals -1, r equals plus or minus I. That'll lead us to our fundamental set. The imaginary is sine of x, cosine of x. Alpha equals 0, beta equals 1. That's my fundamental set. I'm going to write that out. That's also my solution, homogeneous solution, C1. And the order here doesn't matter. So now our YP, U1, Y1 plus U2, Y2, which is actually U1 sine of x plus U2 cosine of x. So this is our Y1, Y2. I'm just going to write the linear setup. We take the derivative. Sine of x is cosine of x. The derivative here times U1 prime, U2 prime equals 0. And our f of x, this is our f of x. So we write 2x sine of x. Okay, so our Wronskian. We need our Wronskian. So it's the determinant, so it's minus sine squared x minus cosine squared x. Remember, we do the diagonal subtract. Factor out a negative. And it looks like the answer is -1. Our W1, 0. We replace the first column, still the determinant we're looking for, with our B. Find the determinant. So that's 0 minus. So we can just drop that 0. My second one. So it's 2x sine squared x minus 0. Let's circle these. So U1 prime is W1 over W. Minus 1, so the negatives are going to cancel. Now also, if you remember, sine of 2x is equal to 2 sine of x cosine of x. That's a trig identity. So I'm going to simplify this to be x sine of 2x. Okay, so U1 prime equals x sine of 2x. And I will integrate both sides in terms of x. And I will get U1 equals, looks like I have to do parts here. So it looks like I have to go U equals x, du equals dx, v dv, dv will be the other piece. Sine of 2x dx, integrate, that's half the negative. And the formula is uv minus v du, so it's uv minus v du. So it's another minus, so it's going to be plus half in the front, cosine of 2x dx. It looks like we can handle that pretty easily. Cosine of 2x, we're integrating, so that'll be 1/4. 1/2 times 1/2. Sine of 2x, and that's positive. And there's U1. Now let's do U2 prime. It's W2 over W. W2 is right here. And I think our W is just -1. So we are going to integrate both sides in terms of x. And you can keep that 2 in there or take it out. It doesn't matter. I'm going to keep it in the front. So whatever I find, I'm going to wrap it. So parts again. X will make that go away. V we got to find. Okay, so we need to integrate sine squared x. We basically have to use the power reducing formula, which is half 1 minus cosine of 2x. Those are equal. So I'm going to integrate that to get v. It'll be half x, that term, and then minus 1/2, divide by a 2 again, sine of 2x. And that looks like it should be positive. This one, but that should be negative. So now the formula, u times v, looks like I need a little bit more room here. It's going to be distributing the x, and then minus v du, the integral of these two. And it looks like I can integrate that now. Then I distribute that, and that's plus 1/8 cosine. I do think that is negative, because this is negative, that's negative, and there's a negative, they're negative. Yeah, there's 3 negatives. And I still need to bring this down. So I need to distribute that too. Is there anything that can add? And that is u2. So putting them together, writing this out, we have y equals yc plus yp. Yc is c1 sine of x plus c2 cosine of x. Yp is u1 plus u2 cosine of x. And we have our u1 and u2 box just up here. Let's write it out. u1 u2 times cosine of x. Yikes. There's my u2 cosine of x, u1, u2, and my y equals yc plus yp, adding those together, my general solution to this non-homogeneous. Plus my yp. There we go. There's my general solution. Okay, I'm gonna stop there, and I'm gonna do a second video on this where I will basically do a problem from variation of parameters, and then I'll also do the same problem using undetermined coefficients. Okay, thanks for watching.